Okay, guys, so this is the beginning of Unit 5, okay? Our last unit on derivatives. So Unit 4 was contextual applications of derivatives, one of my favorite units. And then Unit 5, now we're looking at analytical applications of a derivative. So what do we use a derivative for? Okay, so look at this scenario here. Does anybody drive? You have your own car? Wow, nice. Huh, is that right? So I didn't get a car when I was young. My parents wouldn't let me. Okay, so when you're driving and you see a police like stationary on the side of the road, is it like a yes, right? Even if you're not speeding, because typically I'm not speeding because people are passing me up. But it's like a reflex, and then I look guilty even though I wasn't. Okay, so imagine this situation. Suppose you're driving, okay, and you see, the cop car stationary there. So when you pass this police car, you look at your speedometer, you're going 50. Okay, you're safe. All right, 4 minutes later, you pass a second police car. Okay, you again check your speedometer, 50 miles per hour. You're good. However, okay, distance between two cars is 5 miles. The second police car pulls you over, tickets you for speeding. Not only for speeding, but speeding 75 miles per hour. What do you think? Were you speeding? Think about it. Talk about it. Like, is this ticket justified? Like, were you in fact speeding? It's bad. 30 miles over the speed limit? So if the speed limit is 75, you're driving 105 miles per hour?
It's like 65. I go like 8. When you pass both 45 south. How is one person going to gas in 4 minutes? What was the question? Oh, is it justified?
Yeah. Okay, I'm not asking you, like, is this going to hold up in court? Okay. But were you in fact speeding? According to math. Tell me about the math.
I'm going to say yes because of the mean value.
When your speedometer, like your needle, yeah. Well, go think about it. Like, I want to know, okay, so were we in fact speeding? If this happened? Based on what? Like, how do you know?
Are we in Texas?
Oh my gosh. Okay.
You only have to deal with them one day. I just put that out there.
Then when you weren't here today, they were so much more talkative to me. They get nervous when you hear something. Oh, do you think she's sitting back there like watching you and judging you?
So if I sit up there next to her, you'd be fine?
Yeah.
Because I'm not looking at you when I'm up there?
Yeah, see? But like, APs just sit there like, they always sit by me. I'm like,
Focus on the question.
Mm-hmm.
Yeah.
Based on what? So how? Using what? So guys, how would you determine how fast you were going? Like focus on the what?
but when we pass both.
Correct, because what happens when you see a police car on the side of the road? You hit the brake. So clearly, is it possible we could have slowed down?
If we're passing the car,
So then how can we? Because like this probably would not hold up in court, right? Policeman can't show up and be like, we were exactly 5 miles apart, and it was exactly 4 minutes. I'm giving you some big hints here. So how would we calculate speed? Like, all right, guys, how much distance was traveled? 5 miles. Okay, let me write this down. 5 miles. Yeah. That's true. Good point. All right, so the distance traveled, okay, 5 miles. How much time elapsed, guys? 4 minutes. All right, so typically when you see a speed limit sign, it's not in miles per minute, it's in miles per hour. Can you convert that to miles per hour? So if I want to convert this to miles per hour, how many minutes are in 1 hour? So I can write that ratio, right? Do some dimensional analysis. 60 minutes, 1 hour, minutes divides out. So what's 60 divided by 4? Good. 15 times 5? 75 miles per hour. So guys, if you cover a distance of 5 miles in 4 minutes, on average, you had to go 75 miles per hour, on average. And guys, there's 2 instances where you were going below 75. So to average out at 75 miles per hour, at some point you would have been going even faster. So, was this car in fact speeding? Okay, yes. Now, would this hold up in court? Probably not. However, there are some states that do this. Similar situation. So you said you speed on Beltway 8? Yeah. So, in some northern states, it hasn't happened in Texas yet, they do it with toll booths. Toll booths are stationary, right? They're fixed distance apart, so if you go underneath one, regardless of whether you're speeding or not when you go underneath it, if you make it to the next one too fast, ticket in the mail.
What?
I mean, you're speeding. Yes, way.
I
Some of the...
actually don't have
Okay. So guys, what we just calculated was the average speed, okay? The average rate of change. All right, so this is introduction to the mean value theorem. So guys, when you think of the word mean, what word do we relate with that? Average, okay? So mean value theorem, okay? When you think of the word mean, think of average. All right, so here's what the mean value theorem says. So theorems, they have a hypothesis and a conclusion. If the hypothesis is true, the conclusion is guaranteed to be true. If the hypothesis is not true, we can't make any yes or no about the conclusion, okay? Could be true, may not be true. But if the condition is true, hypothesis, we call them conditions. If the condition is true, the conclusion's guaranteed to be true. All right, so mean value theorem says, if a function is continuous on a closed interval and differentiable on an open interval, then there's guaranteed to be a point, okay? Kind of don't like the way this is written. There's guaranteed to be a point such that the average rate of change, okay, or such that the instantaneous rate of change is equal to the average rate of change. So I'm going to write it like this. F prime of C equals F of B minus F of A over B minus A. All right, so a while ago y'all were having this discussion about the difference between an average rate of change versus an instantaneous rate of change. Okay, so average rate of change over an interval, right? Graphically, we relate average rate of change to the slope between 2 points, right? Slope of a secant line. So here I can give you a graphical representation. So this would be our point A, F of A, B, F of B, and we can calculate the slope between those 2 points. Y2 minus Y1 over X2 minus X1. So that's what this is, okay? So I can relate this to slope of secant line. So the slope between those 2 points. Now, do you agree that this function that we have here, this f of x, is that continuous on this interval? Is it also differentiable on this interval? Okay, no discontinuities, no sharp turns, no vertical tangents. All right, so here's my tangent line. Is there a point in this interval such that the instantaneous rate of change equals that average rate of change? Such that the slope of the tangent line is parallel to the slope of the secant line? Probably happens about right there. So that's your instantaneous rate of change, which graphically, we relate that to slope of a tangent. Slope of tangent. So there's a couple ways that you can remember this. So f prime of c, okay, that's a derivative. Okay, what is a derivative contextually? Okay, that's graphically. What is it contextually? Slope at a point, still graphically, slope at a point. There you go, instantaneous rate of change. So we can say the instantaneous rate of change, just sound it out, equals average rate of change. And then if we want to get really sloppy, we can say I rock equals A rock. Instantaneous rate of change, okay, just an abbreviation. I rock equals A rock, okay. Your calculus slope equals your algebra slope, okay. So what the mean value theorem says, if these conditions are met, if you have a function that's continuous on a closed interval, differentiable on the open interval, okay, there's guaranteed to be a point. Now look at the conclusion. Then there's at least one. It doesn't say there might be, it doesn't say there could be, it doesn't say there probably is. Okay, it says there is. At least one number, C, in the open interval. Okay, in the open interval. So guys, sometimes when you calculate the average rate of change, you'll get a number, a numerical value. Okay, your derivative will be a function of x. So you end up solving an equation for x. Sometimes the equation has multiple solutions. So you're looking for a number inside the open interval. So any numbers that are outside of the interval, we ignore them. Any numbers that are the endpoints, we ignore them. Okay? Because by definition of mean value theorem, it says C will happen in the open interval. Okay? Now, they're never going to give you a multiple choice question where a distractor includes the endpoints. Does that make sense? They're never going to have one without the endpoints and one with the endpoints. But just be careful on a free response question. Ignore the endpoints, okay? By definition, it happens in the open interval. All right, do we have this? All right, so here's another representation for you. So we have a polynomial function. Something you should know about a polynomial function is it's continuous and differentiable everywhere, okay? So I've got a continuous differentiable function, and we can show graphically the average rate of change, so f of b minus f of a over b minus a, related to slope of that secant line. So, because the conditions are met, the conclusion says there's at least one point such that the instantaneous rate of change equals the average rate of change. Graphically, there's at least one point where the slope of the tangent is equal to the, right there, and? So you're saying twice? So, right there, and right there. So this one would have two values of C that satisfy the conclusion of the mean value theorem. So guys, this is the conclusion of the mean value theorem, because a lot of times it's going to ask you, find the value or values of C that satisfy the conclusion of mean value theorem. So this one would have two solutions. Good? All right, so let's look at this function. So we're looking at this function f of x, it's 3 minus 5 divided by x on the interval. We're going to focus on the interval 1 to 5. So first question, how many values of x in the open interval satisfy the conclusion of mean value theorem? So I need to make sure you understand what that means. So this is the conclusion of mean value theorem. Okay, right here. F prime of c equals f of b minus f of a over b minus a. How many values of c satisfy that conclusion? So graphically, we can think about average rate of change as the slope of that secant line. Okay, use your tangent line. Is there a point in this interval? Yes. Okay. So where does it appear to be somewhere in here. All right, so how many values of x in this open interval satisfy the conclusion? So how many solutions would we have? Just one. Okay, so part B, show that the mean value theorem applies. So what does that mean? That's the conclusion. The conclusion is guaranteed to be true if. That's the conclusion. What do we have to do for anytime you're about to use a theorem? What do you have to do? Check conditions. When it says show that the mean value theorem applies, that means you're checking the conditions. You're verifying that the hypothesis is true. All right, what are the conditions? All right, so I'm asking myself, is f of x continuous on the closed interval 1 to 5? Yes or no? Okay, are you basing that on the graph? What if we didn't have a graph? Okay, so I go back to my function, right? Where would I have a discontinuity in this function? What do we look for when we're checking for discontinuities? Algebraically. Division by 0, even roots of negatives, log of non-positives. So I always say there's 3 things we don't do in calculus. Okay, I don't say we can't do them because you can do them later, they're all legal. But in this class, in Cal 1, we work in the real number plane. So we don't divide by 0, we don't take even roots of negatives or log of non-positives. So this function would include division by 0. Okay, what would cause division by 0? At x equals 0. Because 0 is not in my interval, don't care. Okay. Now, if it asks me to apply the mean value, or does the mean value theorem apply on the interval -1 to 5, what would our answer be? No. Okay. Be careful. Guys, can you think of a function that is continuous for all x, but not differentiable for all x? No, I'm just asking for pause for a minute on this. Can you name a function that's continuous for all values of x, but not differentiable for all values of x? Mm-hmm. Pause for a minute. Pause for a minute. This has nothing to do with this question. So think about absolute value of x. Okay. So if we were to look at that graphically, it's continuous, right? Continuous for all x, but it's not differentiable, okay, at x equals 0 because of that sharp turn situation. Okay, derivative on the left, derivative on the right are very different. So does mean value theorem apply to this function on any interval that captures 0? So look here. I can draw my average rate of change, and I can use my tangent line. If I slide it along, is there any point in this interval where that tangent line is parallel to the secant line? No. Okay? So mean value theorem would not apply on any interval that contains 0. Now, if I were to try to apply mean value theorem on the interval 1 to 5, would it apply now? Yes. Okay? So you got to check the interval in question. Okay? Now, there is a discontinuity on this function, but it happens at x equals 0, which is not in our stated interval. Okay? Now, I'm going to tell you this, guys. Check your conditions. If you try to apply the mean value theorem over an interval where it doesn't apply, you're just going to get very frustrated. Okay? Sometimes you might even get a number. You think it's a solution, but it's not. Okay? And then other times you'll just get really, really frustrated. All right, so is this one continuous on the closed interval 1 to 5? Check. Okay, my only issue, division by 0. Check. All right, and then I ask myself, is f of x differentiable? Differentiable on the open interval 1 to 5. How would I verify that algebraically? Find f prime. Perfect. I'm going to use this space right here to find f prime. All right, what's f prime? What's the derivative of 3 with respect to x? Y. Perfect. This is a constant. All right, what's the derivative of -5 over x? know I'm not doing this the most efficient way. 5 over x squared. Okay, so one of the derivatives you probably should have memorized just because it comes up a lot is the derivative of 1 over x. Rather than having to apply quotient rule or rewrite that as x to the negative 1, just have that one memorized as negative 1 over x squared. Because, so, it's the same thing. If I were to rewrite that, you get x to the negative 1. And then use power rule negative 1 times x to the negative 2. And then bring that power into the denominator, change the sign of the exponent. So that one appears a lot. I definitely don't want to have to waste time doing quotient rule. I want to avoid that extra step of rewriting it and then rewriting my answer. So that one you just might want to have kind of able where you can recall it very quickly. All right, so this is just negative 5 times 1 over x. So our derivative would be negative 5 times negative 1 over x squared. So 5 over x squared. So where does my derivative not exist? At x equals 0, okay? We know the function's not continuous at x equals 0, therefore it's also not differentiable, but I can also verify that algebraically by looking at the derivative. All right, so, however, is it differentiable for all values in the open interval 1 to 5? Check. All right, so show that the mean value theorem applies. That means check conditions, 1, 2 conditions. All right, and now it says find the value of c that the theorem guarantees. All right, so now we're going to find the values that satisfy the conclusion. All right, so the conclusion says, all right, so therefore there's guaranteed to be some number c in this open interval, some x coordinate that we call c, such that the derivative at c is equal to the average rate of change over the interval. So that would be f of 5 minus f of 1 over 5 minus 1. All right, what is f of 5? Okay, so we can look at that graphically. So this is a 0.52, or I can quickly make a substitution. 5 divided by 5 is 1, 3 minus 1 is 2. And then what's f of 1? Negative 2. Okay, I can see that graphically, or quickly make a substitution. 3 minus 5 is negative 2. All right, so f prime of c equals f of 5, 2, take away negative 2 over 4. All right, what do we get when we clean that up? 1. All right, and f prime of c, that just means we take our derivative, make a substitution for x. Okay, so this would be 5 over c squared. And we solve for c. How do I solve for c here, guys? This equation right here. Multiply by c squared. Can we do that? Multiply both sides by c squared. All right, so I've got c squared equals 5. And then take the square root. So square root of c squared is the absolute value of c, square root of 5. So I end up with plus or minus 5, okay? I need you to understand that this equation has 2 solutions, okay? The solution to this equation is plus or minus square root of 5. However, what does the conclusion of mean value theorem say? There's at least one number c in the open interval, okay? And we already said, how many solutions does this have? 1. All right, so what are we going to ignore? The negative. Okay, so ignore that negative. C equals positive root 5. Everybody okay there? And if we had a solution that was at an endpoint, we need to ignore that value as well. Everybody okay? All right, so let's look at this next one. All right, so if the conditions for mean value theorem are met, determine the value of f prime of x that the mean value theorem guarantees. All right, so this problem's worded differently, and you got to pay attention to this. Is it asking me to find the value of x or c that satisfies the conclusion? No. It's just saying determine the value, okay, of f prime of x that's guaranteed by the mean value theorem. There you go. That's it. Yes, ma'am. Okay, so let's verify the conclusions real quick. or sorry, the conditions, conditions, if the conditions are met. So what's the first condition? All right, so is this continuous on the the closed interval, -1 to 1? You have a polynomial function. Okay, so you're looking for, will we ever be dividing by 0, taking even roots of negatives or log of non-positives? No. So is this continuous on the closed interval? Check. Okay. Guys, all polynomial functions are continuous and differentiable everywhere. All right, so is this differentiable? On the open interval? Yes, due to the fact that it's a polynomial function. All right, so if the conditions are met, the conclusion is guaranteed to be true. So it says that f prime of c equals f of b minus f of a over b minus a. So guys, it's saying determine the value of the derivative that is guaranteed by the mean value theorem. So guys, there will be a derivative that is equal to this average rate of change. So in this problem, you're finding average rate of change, and that's it. Okay, like she said, find a rock. All right, so C equals f of 1 minus f of -1 over 1 minus -1. All right, so you're just doing some arithmetic at this point. We need f of 1, and we need f of -1. So what do we get? I think this question's on here. So what's f of 1? 1 minus 1 minus 2. Is that right? Is that -2? Yeah? All right, what about f of -1? Is it 0? Yes? Okay, I'm trusting you. All we're doing is arithmetic, right? All right, so I just make that substitution here. So f prime of c, f of 1, -2 minus 0, divided by 1 minus -1, which is 2. So -1. And that's it, guys. There's guaranteed to be a derivative that equals -1 at some x value in that open interval. Okay? That was cool. And guys, so we'll come back and work that trig function, but this is a multiple choice question straight from the test, straight from the AP exam. And the reason I put this on here is because I got very, very frustrated when I was trying to solve this problem for the first time. Okay, I remember exactly where I was, sitting in the office of an eye doctor waiting for my husband. And I was getting so frustrated on this problem, I literally wanted to throw a magazine across the room. So, and it's because I didn't even finish reading the problem. I was so used to seeing questions that tell me to find C. Okay, so when I got here, the mean value theorem guarantees a value C, so I started trying to find C. So I found the average rate of change, I set it equal to the derivative, I got this function that wouldn't factor, I could tell my answer was supposed to be an integer. I was so angry. And then I was like, oh my gosh, doesn't want me to find C. Just wanted me to find the average rate of change, and that was it. And I had done that a long time ago. So read the question and make sure you understand what it's asking you for. Okay? All right, so let's look at this trig function. So first of all, determine whether or not the conditions are met. If the conditions are met, we do want to find the value of C that's guaranteed by this theorem. All right. Same thing we did. All right, so what are the conditions? Okay, so is this continuous on the closed interval? Okay, 0, 2 pi? Do we know what that looks like graphically? One cycle of your sine curve. So 0 to 2 pi. That's a pretty good graph. I'm pretty impressed with that. All right, so is this continuous on the closed interval 0 to 2 pi? Check. All right, is it differentiable on the open interval 0 to 2 pi? Okay. So what are the three situations for which a function is not differentiable? So any discontinuity, okay, any sharp turn situation, including a cusp. The last one's one I always forget also. Well, okay, I know what you're thinking. If they were semicircles, then it would have that vertical tangent. This is a sine curve. It should be more curved. So any discontinuity, okay, any type, any sharp turn situation where the derivative left and right are different, or any vertical tangent. So none of those situations apply here. My derivative exists at every point, so we're good. All right, so if conditions are met, I move forward. Okay, so it says find the value of c that the theorem guarantees. All right, so there is some number c, at least one number c, such that the derivative at that value c is equal to the average rate of change. So f of 2 pi minus f of 0 over 2 pi minus 0. You know what? You got a new computer, right? It's so much easier to write on your board now. Yeah. Yeah. All right, so what is f of 2 pi? So f of 2 pi, so we're talking about the sine of 2 pi, which is 0. What is f of 0? So sine of 0 is 0. I can see that graphically. So if I think about the slope of the secant line, we're looking at a horizontal line. Okay. All right, so this means, no, I'm going to go vertically. All right, so f prime of c equals 0 minus 0 divided by 2 pi, which is what? 0. We just said that, right? Horizontal line has a slope of 0. All right, so now I need the derivative. So what is the derivative of sine x? Cosine x. So all we're doing, we make a substitution for x. Okay, we call it c. Guys, if you forget to replace it with c and you just solve for x, that's fine. They'll just ignore that. All right, so cosine of c equals 0. So what angle or angles have a cosine ratio of 0? Say it again. Pi over 2 and 3 pi over 2. So two solutions. Is that reasonable? Okay, based on the graph. So here's your tangent line. So do we agree that it happens right here at this maximum, which is pi over 2? And then keep going right here again at this minimum value, horizontal tangent, which is 3 pi over 2. Okay? Everybody okay with this? Any questions? All right, moving on. Let's look at number 3. What time is class over? All right, 5 minutes. Okay, so here we go. X equals, f of x is x to the 2/3 power. Anybody know what that graph looks like? All right, so we got to think about this algebraically. Okay, so is this continuous? On the closed interval, -1 to 1. So think about it. When you're thinking about discontinuities, you're thinking about values of x not in the domain. So I'm running through those three situations. Will I ever be dividing by 0? No, because I don't even have a denominator here. Will I be taking the even root of a negative? No. Take an odd root, right? My root here is odd. I can take odd root of any number, so we're good there. Any logs? No. All right, so continuous on the closed interval? Check. All right, what about differentiable? Well, guys, a lot of time I think about this graphically, but we don't know what this graph looks like, so we need to do this algebraically. we do need to look at the derivative, or take the derivative. All right, so help me out. What's the derivative? 2/3. Okay, so I'll start there. 2/3 times x to the negative 1/3. So this is 2 over 3x to the 1/3. All right, so will this derivative ever not exist? When what equals 0? So when x equals 0, because then I have division by 0, it's not differentiable, okay? So, no. And guys, even power over odd root, you've been using the word cusp a lot. This is a cusp situation, okay? So even power over odd root creates a cusp where it looks like this. And by definition, a cusp is where on one side the derivative is going to negative infinity, and on the other side the derivative is going to positive infinity. Okay? So this is a cusp situation, so I can't move forward because mean value theorem does not apply. So mean value theorem does not apply since f of x is not differentiable at x equals 0, because 0 is captured in our interval. If they were asking me to apply mean value theorem to an interval from 1 to 10, could we do it? Yes. Okay. But any interval that captures 0, mean value theorem does not apply. You're welcome.